Hello, in this video we're going to go over section 10.2 on calculus with parametric curves. First, let's talk about the definition of tangents here when we have a differential curve. So we have that f and g are going to be differential functions that we use to define a curve as x equals f of t and g equals g of t. And then we want to find the tangent line of a given point for this curve. Because f and g are differentiable, then x and g are also going to be a differentiable function, and y is also going to be a differentiable function of x. Then by the chain rule, we have that dy dt is going to be equals to just dy dx times dx dt. So this is just coming from the chain rule, in that we're assuming that y is also a function of x, but x is a function that depends on t. Now we can use this arrangement to just find a definition or a way that we can express the y in terms of the x, so the variation of y with respect to x. So if we assume that dx dt is different from 0, we solve for dy dx, and then we're going to find that just dy dx is the ratio of the derivatives. We have the ratio of dy dt over dx dt, and of course this is going to mean different things for everything that we usually do. If we want to consider a horizontal tangent, then that happens when dy dx is equal 0, then that's going to be translated into just dy dt being equal 0. Also, the second derivative is just going to come and be the derivative of the second derivative of y dt divided by dx dt. Now, let's see this in practice. So, assume that you have a curve that is defined by the parametric equation x equals t squared and y is equals t cubed minus 3t. So first we want to show that the curve C has two tangents at the point 3, 0, and find the equations. We want to find the points where the tangent is horizontal or vertical, and we want to determine where the curve can be concave up or down. And finally, we want to sketch the curve. So now let's go here and find some of this things. So the first thing is, of course, finding out the y dx. So by definition, we just stated that the y dx was going to be dy dt divided by dx dt. And this is just a derivative of each of these things. So the dy dt is just going to be the derivative of this with respect to t. So it's going to be 3t squared minus 3, and the derivative of x is going to be 2t. Now, if we have that C has two tangents at the point 3, 0, remember that this is x and y, and is 3 dot 0. So this means that t squared is equals 3, because x is t squared, right? So t squared is equals 3, and y is equals 0. This is what we're getting from here. X equals t squared is equals 3, y is equals 0. So from this we have that we have 2 points where we should be caring for this. T equals plus or minus the square root of 3. Now this means that we're going to have 2 different points where the curve crosses 3 points here, which is in t equals 3 and t equals minus the square root of 3. And this means that there is self-interception of the curve. Now, going into a little bit more detail here, these 2 points are going to define the slope of the tangent lines ones that I plot here. So if I plot when t is equals to the square root of 3, then the y dx, sorry, this is going to be what happens when I plug a square root of 3 here. So notice the square root of 3 square is just going to be 3. So this is 9 minus 3 is going to be 6 over 2 square root of 3. So this is going to be 6 over 2 square root of 3. And now also when t is equals minus the square root of 3, a similar thing is going to happen, and we have that the y dx is just going to be minus 6 over 2 square root of 3. So this is the similar calculations that we get from there. Now at this point, this is, if you remember how to get tangent lines, this is just going to be the slope. So this is either m1 and m2, and we have the point 3, 0, so we can go with the y minus y0 equals mx minus x0, and that's going to give me the slope. So this is going to be y is equals to a slope, and in one case is going to be this 3 over square root of 3, which is what you get from simplifying this, or simply, if you even simplify this more, you can see just this as a square root of 3. This is just a square root of 3 x minus 3. And so this is for when we have this slope. Similar here, 6 divided by 2 is 3, minus 3 over square root of 3 means that this is going to be negative square root of 3. So the second line is just going to be y equals minus the square root of 3 x minus 3. And so now this is giving me the two different tangent lines that I have when we are at the point 3, 0. So this is pretty much A of our questions. Now for B, we want to know when the y dx is equal 0. So this means that we want to know when the y dt is 0, because that's pretty much the top, and that's when this is made 0. So that implies that 3 t squared minus 1 is equal 0, or this implies that t should be equals plus or minus 1. And so that corresponds to two different points. If we go back to the original curve, remember that we are on the curve x equals t squared and t cubed minus 3t. So if we plug those points in, we're going to get that we are at two different points. We are at the point 1 minus 2, and we are at the point 1 minus 2. Remember x being t squared, that's why with t equals 1, this gets me 1 in both cases, and finally it gets me 1 minus 2, 1.2. So those are the two different points where the slope is just going to be horizontal. Now for the slope to be vertical, so this is horizontal tangent. Now vertical tangent, means that the bottom is going to go to 0. So the x dt which is equals to 2t is going to be equal 0. So this is just implying that t equals 0 is the point where we're going to have the vertical tangent. And so this implies the corresponding point is just 0, 0. Now we also want to determine where we have the function is curve concave upward or downward, and this is mostly done by finding out what the second derivative is, since the second derivative is what's going to give me information about concavity. So C, concavity. And so remember, we want to find out what the second derivative of y with respect to x is going to be. And by definition, this is just the derivative with respect to time of the y dx over dx dt again. But then applying what we have, we already have the derivative. This is the derivative with respect to t of 3t squared minus 3 over 2t. This is what we got on the first, when we got the first derivative, and then divided by 2t here. Now, if I do a quotient rule here, then this is going to give me, at the end when simplifying, 6t squared plus 6 over 4t squared over 2t. Or if I just simplify this a little bit more, this is going to be 3t squared plus 3 over 4t cubed. Okay, and so because of the nature of the top and the bottom, notice that the top is always going to be positive and the bottom is always going to be dependent of the sign being a cube. So we can say that if t is bigger than 0, then this is going to be bigger than 0. And so this is in this point is concave upward. And if t is less than 0, then as you can see, the bottom is going to be negative as well here. And so we're going to have that the y dx squared is going to be less than 0, and this is going to be concave downwards. So a lot of this is just put the curves in terms of what we already know of the original calculus. So all the things that we normally do in calculus, find the equation of the tangent line, and then find concavity. Now, with all this information at this point, we can probably sketch what the curve is going to look like, get some information on it, especially from the part B and C. But to simplify, I'm just going to show you what it looks like here and contrast that with the information of what we know. Since of course it's very difficult just to obtain values particular values to get some points, but this is the strategy that you're probably going to be able to make. You know that at the point when t is a square root of 3 and minus the square root of 3, then it crosses and it's 0 here. Then you have this self-crossing here. You know that also at t equals 0, this is going to be 0. So these are some of the points that you're plotting with this. And then of course we have information like, well, if t is bigger than 0, this is going to be concave up, and so this is where these points here are being represented. And when t is negative, the representation is with these points. You can see that the direction of the curve is coming from here, and then it's going over here, and then going over here. So that's the direction of the curve for this particular example. Now, the next things that we can define are what are area, arc length, surface area, and how to deal with this in a parametric form. So let me first state what are each of those things, and the next video is going to deal with actually seeing examples of how to work out with that. So first, notice that the area is giving us the integral for a particular function f of x that has x defined as f of t and g equals g of t, and t moves between alpha and beta. We have that the integral of a to v of the function f of x is just going to be transformed into the integral of a to b of y dx by the area function, and that's going to be equivalent to just doing the integral of alpha to beta of g of t by f prime of t dt. Now, in a similar fashion, the arc length function that we have from before, if you remember, this was the integral of a b of the square root of 1 plus the y dx squared dx. And if we use the chain ruling here, then you're gonna find out that you have a very similar formula. Now this changing what y is in terms of t using f and g. This is going to give me by the chain rule that the y dx can be seen as the y dt over dx dt square. And so simplifying that and changing dx by dx dt times dt, then we can see that this gets simplified to the integral of alpha to beta of just the square root of the derivative dx dt square plus the y dt square, and we're integrating all that with respect to dt. So it's a very simple formula for arc lengths as well. Similarly, surface area is going to have a similar transformation. If you have the formula for surface area that we were working before, now that formula is going to be transformed to the integral of alpha to beta of 2 pi y, the square of dx dt square plus the y dt square. Okay, so next we're going to see some examples of how this works.